Okay, you guys, so let's go ahead and jump into organometallic reactions. And so when I mean organometallic reactions, I'm not talking about let's jump into the Heck and the Suzuki um, and the Stille reaction. In order to talk about those reactions, we have to learn about the very basic reactions. Just like when we talk about the aldol or amine, enamine reactions, we need to know SN2, SN1, E2, E1. Same thing in organometallics. We need to start with the very, very basics before we can jump into those more complicated systems. And so um, let me first introduce oxidative addition. Okay. And so oxidative addition looks as follows, and I'll explain things as I'm going along. So a couple of things first. M is, of course, our metal. That's how we've been denoting it throughout lecture 6 and the first part of this lecture. L means our ligand or substituent, however you want to call it. Okay. N means the number of ligands, of course, on the metal. Okay. And then finally, AB is our organic molecule. And it can be polar or nonpolar. So it can have a dipole or not have a dipole, right? If it has a dipole, it's polar. If it doesn't have a dipole, it's not polar. So a couple of things when it comes to oxidative addition. Let me highlight this. Usually the metal is electron rich. So it must have d electrons. Which in turn, of course, means that it cannot be D0. It cannot come in with no electrons whatsoever. And finally, not surprisingly, the complex, LNM, must be unsaturated, less than 18 electrons. And we talked about this in part 1, right? We said, hey, if it has 18 electrons, it can't do anything. So it shouldn't come as a surprise that it has to have less than 18 electrons in order for it to proceed and do an oxidative addition reaction. Now, you've seen oxidative addition reactions before. This isn't anything new. We just never called it that. And so from Chem 24 to 124, we actually talked about this reaction a lot. You can have an aryl halide or a vinyl halide or alkyl halide. Remember, vinyl just is a fancy word for alkene plus magnesium metal. Introduces the magnesium in between the alkyl or aryl or vinyl group and the halogen. And this is, of course, a Grignard reagent. Right? Please notice how similar it looks. You come in with your metal. You've got your organic molecule. In this case, it has a dipole. So it's a polar organic molecule. And the metal inserts itself between that bond. The metal inserts itself between the R group and the halogen. This is oxidative addition. Of course, because the magnesium is a metal, it's 2 plus, R minus, and of course, X minus. Okay. So very similar to this Grignard reaction, Grignard formation. Okay. We're just using transition metals now instead of first and second column metals. So, for example, we've got the following palladium complex. This is palladium 0. So there are 10 electrons. There's 2 triphenylphosphines for a total of 4 electrons. So this complex has a total electron count of 14 electrons, which means that it is unsaturated. Plus aryl bromide. This is a polar molecule. You can draw out the dipole. And just like with our Grignard formation, the palladium inserts itself between the aryl system and the halogen. Please notice that now my palladium has a 2 plus charge, D8 electrons. I still have my 2 triphenylphosphines, 4 electrons total. My 1 bromine, 2 electrons, and my aryl group, 2 electrons, for a total count of 16 electrons. So I haven't gone over my 18 electron count. I'm okay. Again, my palladium has inserted itself between my aryl and my halogen, just like it does in my Grignard reaction or reagent formation. Okay? So let's talk about the groups it inserts in between. Let's talk about our AB group. I've shown you an example of an aryl bromide. Let's talk about that. AB groups. Because we said that they could be nonpolar or they could be polar. Okay? Let's talk about the polar groups because they're the most popular. Like I just mentioned, you can have alkyl halides. Etc. You can have vinyl halides. You can have aryl halides, just like we did in our previous example. You can actually use acids, specific halogen acids. You can also use acid halides. These are probably the most popular polar compounds or polar groups that you can use. Now, it's theorized that the mechanism is an SN2 mechanism when it comes, or an SN2-like mechanism when it comes to these groups. And so what do I mean by this? And what I mean by this is that the metal usually comes in with at least 2 electrons. So must have at least 2 electrons. Okay. You introduce your organic compound. And again, we're just talking about organic compounds that are polar, right? We're not talking about nonpolar compounds. It's assumed that the metal attacks, kicks off the electronegative atom, and you've got your intermediate. Oh, excuse me. And of course, the leaving group that you just made. And the leaving group comes back and attacks its metal to form the oxidative addition product. So it's sort of an SN2 because the metal attacks the backside. You've got your leaving group that leaves from the front. And the only difference is, of course, that the leaving group comes back and complexes to the metal. Okay? And that's your oxidative addition product. Now, with nonpolar groups, the mechanism is slightly different. So let's talk about nonpolar groups. Nonpolar groups, oxidative addition is super hard. And that's because nonpolar groups include hydrogen-hydrogen bonds, i.e. hydrogen gas, alkanes, carbon sp2, bonded to hydrogens, so alkenes, or aromatic systems. Now, if you remember from Chem 124 and Chem 24, carbon, hydrogen have very similar electronegativities. Okay. They're not vastly different. And because they're not vastly different, there's no dipole for them, right? You can't draw a dipole or a partial positive, partial negative on one atom over the other. And so because they're pretty similar in electronegativities, they're pretty strong bonds. And so because they're pretty strong bonds, it's really hard to introduce anything in between them. They're pretty hard to break. Okay. And so there are very few research groups that have been able to do oxidative additions into these nonpolar groups. One of them is Christina White at the University of Illinois, and she's become really popular when it comes to the activation of these nonpolar groups. And she's tried a variety of transition metals, so she would be really great to look up. Her name is Christina White at the University of Illinois. I want to say it's Urbana-Champaign, but if you look her up, it's not hard to find all her articles. She's done an amazing job with the activation of nonpolar groups. Anyway, for these nonpolar groups, the mechanism is not SN2-like, right? For an SN2 reaction, you need a polar molecule. You need a leaving group. And this doesn't have a leaving group if the electronegativities are the same. And so it's thought of as a concerted mechanism, a one-step mechanism. And it's a little overwhelming in the sense that when you have your metal and you treat it with your nonpolar compound, whatever that nonpolar compound is, the metal coordinates to the hydrogen bond. So metal coordinates to hydrogen single bond. And as a result, bonds are being made and broken at the same time. And it looks as follows. So as the bonds between the metal and the hydrogens and each individual hydrogen are being made, the bonds between the hydrogen, which I'll draw in red, are being broken. And so this is being broken, and these are being formed. And so this is a one-step concerted mechanism, right? Bonds broken, made in one step. And these bonds are known as agostic bonds. They're not fully formed bonds or fully broken bonds for that matter. And then, of course, you introduce the metal in between your nonpolar compound and the insertion. Because the bonds are being made and broken at the same time, the insertion has to be cis. Okay. So again, this is probably one of the toughest things just because nonpolar bonds are really strong and really difficult to break. And because they're difficult to break, it's really difficult to insert a metal in between those bonds. So that's reaction number one. Reaction number two is reductive elimination. And reductive elimination, luckily for us, is just the opposite of oxidative addition. So if we look at our oxidative addition, if we look at our oxidative addition product, it is just the complete opposite of that. We're just moving backwards. RE is reductive elimination, moving backwards. So just like before, if this was a metal 2 plus because of our oxidative addition, now we have our metal complex and our organic compound. Please notice that for reductive elimination to occur, A and B must be cis. They must be pretty close to each other in order for them to form. And the reason for that is that they believe that the transition state looks very similar to what I just showed you. There are agostic bonds where bonds are being formed and broken now. before they give you your product. And so in order for the bond to be formed between the A and B atoms or groups, they have to be cis to each other. Right? If they're on complete opposite faces of the metal, they're never going to be able to form that bond between them. So they have to be cis. And let me give you a few examples of this. And what I'll do as I'm going through the examples is I'll also give you the electron count of your complexes. Re is reductive elimination. This is palladium 2 plus, which means that there are 8 electrons. There are 2 triphenylphosphines, 4 electrons, 1 aryl group, 2 electrons, 1 vinyl, 2 electrons for a total of 16 electrons. Okay. I'll call this A, and I'll call this B. Okay. If it's reductive elimination, of course, you want A and B bonded together, and that's exactly what ends up happening. A and B are bonded together. This is the new bond formed. That's A and B, plus, of course, our palladium, right? Our metal ligand. And this is 14 electrons. And that's it. That's our reductive elimination. Notice how they have to be cis to each other. Okay. Now, the beauty of this is, of course, that you're forming a carbon sp2, carbon sp2 bond. This new bond and it is incredibly rare, almost impossible to do this without a transition metal, right? You rarely, if ever, form carbon sp2 bonds, rarely without a transition metal. The other beauty of reductive elimination, and I'll show that in my next example, is that it retains stereochemistry. So, for example, reductive elimination, you of course get your ligand. Notice how A and B have to be cis to each other. But please also notice that this is the carbon and the methyl group where they're going to attach, where they're going to bond. And it's already a set stereocenter. And so you form the new bond, but you don't lose stereochemistry. Really clever, because if you remember from Chem 24 and 124, anytime you have a stereocenter and you break a bond and you reform a bond, you typically get the racemic mixture. This says, nope, you're fine as is. were set to form a new bond without losing the stereochemistry. Let me do a few more or one more. Reductive elimination. You've got your A and B. You notice that they're cis to each other. So it shouldn't come as a surprise that you're going to form your palladium with its ligands complex and a new bond between the carbonyl carbon and the ethyl carbon. And so you have formed a ketone. So what you'll find, and this won't always be the case, but what you'll find in the Heck and the Suzuki and the Stille reaction is that typically you start with oxidative addition. The mechanism starts with an oxidative addition reaction, and the mechanism ends with a reductive elimination reaction typically. Okay. So typically, again, the reductive elimination step in the Heck, Suzuki, Stille, or other reactions is the last step, whereas the oxidative addition is typically the first step. And so we'll go over all of those mechanisms and start labeling everything. But these are probably the two most important steps. The third reaction is transmetallation. Okay. And transmetallation is the exchange of ligands between metals. So if it's an exchange of ligands between metals, then not surprisingly, you are going to need two metal systems with different ligands. Okay. So you've got your first metal complex with its own ligand and your second metal complex with its ligand. And all they're doing is exchanging ligands. Okay. Now the mechanism is thought to be one step, i.e. concerted, with agostic bonds as well, in where they're thought to line up. And so if you notice, they're fully lined up with each other to start forming and breaking bonds. And so it looks like a cyclic structure, where not surprisingly, bonds are being formed while bonds are being broken. To form your products. Okay. So what's being exchanged? Now, typically halogens are really great at exchanging. So when you have a halogen bonded to your metal, your leaving group, these are the best to exchange. So for example, we've got the following molecule, okay? And of course, the following molecule is typically derived through an oxidative addition. Aryl bromide plus our triphenylphosphine palladium system. So this is our oxidative addition product. Notice that there's a halogen, and it's typically what is exchanged. You treat it with another metal system. And some of the more common metal systems are boron, tin, copper. In this case, when it's a boron system, this is known as a Suzuki reaction. Now, this is only part of the mechanism of the Suzuki reaction. Okay, I'm not expecting you to know the Suzuki reaction. This is just an example of the transmetallation step in the Suzuki reaction. So you have your transmetallation, where the boron and the palladium exchange ligands. So the vinyl group took over where the bromide was on the palladium, and the boron is now bonded to the halogen. So they've exchanged ligands. And this is, of course, transmetallation. Okay. We'll talk about the R groups later on, but why, Dr. Lucero, why did the R group not exchange? We'll talk about it when we get to the Suzuki reaction. Okay. But what I want you to notice is that now it is set up so that they're cis to each other and it can do a reductive elimination step. But since we're not talking about reductive elimination steps anymore, we won't move forward. This is just an example of transmetallation. Let's do another example. And what I'll do is I'll continue to use the same palladium complex. Now we'll use tin. As our metal. And just like before, transmetallation. It's the halogen and the vinyl group. And again, if you notice, it's cis, and my tin takes on my halogen. This is part of the Stille reaction, the transmetallation part of the Stille reaction. Example. You can also do it with cuprates. You can do the same thing with copper reagents for the transmetallation. And of course, regenerate your metal. Excuse me. And so what I want you to see is that All you're doing is exchanging ligands between metals. That's it. And typically, what you're always exchanging is a halogen. Okay. As we get into the main reactions like the Suzuki, the Stille, the Kamada, the Castro-Stevens, it'll become more obvious and we'll talk about why certain groups exchange over the others. For now, you just need to know that transmetallation means the exchange of ligands. Okay. Okay, I'll go ahead and stop here for this part, and then I'll continue with the last couple of reactions in the next part of this lecture.